Good morning, students. I hope yesterday's class was good and you were able to explore more about the 3D printer and its basics, its history, and all of those. Okay, today we will explore the structure, function, and interrelation of the systems and components of 3D printer hardware, software, and materials. While you probably have used any number of mechanical devices without thinking much about the various systems and components that make them work, here are three scenarios where knowing how your desktop 3D printer works can be a real advantage to you. Preparing your job files, performing basic maintenance, repairs, and calibration, and pushing your machine to its limits. Our incredible journey together explores a component and system that make up a desktop 3D printer. I will be focusing on FFF or fused filament fabrication extrusion printers here. The sequence of subsystems, while there are a number of ways where you can divide up a 3D printer into systems, I have opted to divide the anatomy of these three simple groups: control system, mechanical system, and the last, extrusion system. Well, I will also do an anatomy of what I consider a software system. We will look a bit at the physical layout of the code and file formats. But since that topic isn't exploring physical hardware, let's put it aside for a moment. All the critical physical elements, which where software interacts with the machine itself, are already incorporated into these three systems. Let's start with the control system. The control system covers everything involving electronics, power, signal processing within the machine, including these subsystems and components: interface control board, firmware, power routing, signal routing, and network management. Now let's look at the mechanical system. A mechanical system groups everything to do not only with motion but the chassis on which everything is mounted, and when applicable, the enclosure that shields the machine from the surrounding environment. The primary subsystems and components we will explore here are the motion mechanical subsystems, the build envelope, the frame, case, and enclosure. Finally, we will talk about the extrusion system. The extrusion system starts with the insertion of the filament and follows all the way through the molten plastic, reaching the build platform. The extrusion system includes a number of subsystems and components that we will look at individually: material, feeder, HOTEND, active cooling, and the build platform. Now, getting the print started, here's the most important thing to remember. The role of each component and subsystem can fairly easily be sorted in control, extrusion, and mechanical system roles with a few overlaps. However, when you use a 3D printer, all three systems operate simultaneously and in tandem with each other. In fact, none of the system can accomplish any of their goal without assistance of the other systems. For example, the control system might happily issue instructions into the void without the mechanical and extrusion system. However, it will expect and require sensor data back from the elements hosted and activated by the other system to confirm advance those instructions. So, our story of 3D printing anatomy must begin with acknowledging the need of these three systems to interoperate. And this arrangement cuts both ways. These systems cannot operate in isolation, nor are these three systems so completely integrated into each other that an error in one of these three aspects of the machine will be immediately recognized and responded by the other. Though thanks to the clever firmware design, identifying the type of error from unusual sensor data report can grant you a bit more visibility of one system into another. For these three systems to interoperate successfully, they require the correct initial conditions to be met. Well, that's your job. It's up to you to deliver an accurate and reasonable job file to load and configure the correct printing material, nozzle, build plate, and better adhesion strategy. And when you do your job well, observers experience like illusion of the machine as a single, seamlessly integrated system. The easiest way to tell this story and start off both the print and your journey through the 3D printed anatomy successfully is to step through the preliminary actions leading up to the moment that you hit the print to start fabricating your object. Actions that will jump around among each of these three systems. Okay, so now let's move on to our next topic. Before we move from system to system through the main topics of desktop 3D printer anatomy, let's focus briefly on the process of starting a print. This may be best served as an overview of printing before dividing into each area individually. Loading materials, we are going to jump to the extrusion system to start with our preparation with a preliminary step that takes place just before we print the part. Loading the print material. Before the 3D printer is ready to execute our printing request, we need to load the filament we will use to fabricate the object. This sounds obvious, but you would be surprised to know how many busy 3D printer operators forget to check how much material they have left on their machine and doesn't look to see if the nozzle mounted on the machine matches their filament. Today I am going to take it easy and just select Ultimaker silver PLA that I typically use to print this little robo character. I'll check that I have the correct code installed and get started at this point. If I wanted to shift to another nozzle size, or if we setting the machine for the first time, I'll go through a different process. I'd go through a process of removing and installing new code or running a manual bind build plate calibration process to confirm that everything is at its greatest baseline for printing. Okay, now cleaning the build plate. Here's another moment where the mechanical system meets the extrusion system. If you do not confirm that you have removed the last printed part from the build plate along with any detritus, there are chances the tool head blissfully plowing into the printed object. Your 3D printer needs you to take a second and clean and prepare the plate for a new print. Or the results from the broken tool head to part slipping off the plate will be on to you, because I have selected a silver PLA and because borosilicate heated glass plate for this machine is already suited for printing PLA with no extra films, coatings or glue required. I just need to confirm that the plate is clear of parts, cleaned of residue from past print jobs and free of the natural oils from finger touching the glass surface. Now let's head to the control system. The interactive interface subsystem. Next, now we are ready to start the specific job in the control system. Starting with an interactive interface subsystem. The interface is typically the primary control to use. The interface is typically the primary control you use to calibrate, operate, service your printer. In some cases, it complements the computer control, the device, and in other cases, it replaces computer control entirely. When you are ready to run a job on a 3D printer, your first steps are here at the front of your machine. The core components of the interactive interface subsystem are the display itself, a way to see what options you are activating, as well as other additional information posted by the system about its temperature, printing progress, and job file options. The control buttons, your physical point of contact with the electronics, a Java file delivery process, typically an SD card, USB drive, or USB or an Ethernet cable, the means for getting the job files queued for fabrication, an interface menu for other UI strategy that an operator can navigate to achieve the intended goals, maintenance utilities, usually within the interface menu itself, which allows an operator to update firmware, perform initial or additional calibration stages, and manage materials. Loading and unloading and profile setting and other aspects related to the baseline of the machine. I use the interface to load materials to install Silver PLA, and now we are ready to run our print. We navigate through the print menu to locate our file and select it. Many times this is the last intervention you will have with the machine until you collect the final print. Minutes, hours, or even days later. But we are going to explore in greater detail what happens next and the systems, subsystems, and components involved. Control system. While the interactive interface subsystem might be the system you interact with physically and the one that provides you evidence as to what processes are taking place in the machine, the control board locked away in the base of the machine is really the one calling the shots during the printing process, because the control board electronics coordinates all the power signal, motion, cooling. All of these other elements of the control system deserve their own separate consideration as a part of the portrait of the control board electronics. Any discussion of the control board subsystem may end up overlapping significantly with the other elements within the control system. In terms of anatomy, I'd say that the main board electronics behave a bit like the heart, brain, and circulation system. It touches on just about everything that happens. When we select and activate the print job in the interface, this action triggers the control board to start the printing process, unspooling a series of actions across the electronics. From diverting power to preheating for the heated bed and toolhead to reading through the initial pre-print commands and settings in the G-code file or onboard in the firmware. The interface only plays the role of the messenger. Now the real orchestra tunes up in the poised for action. This material requires a heated bed, so preheating of the bed and nozzle happens during this stage. The time to heat these elements depends upon the environmental condition. You can never fully predict the temperature of the electronics draw required to reach the target state. Establishing home and auto-calibrating the build plate. Let's continue, but now from the perspective of the mechanical system. As soon as the job is selected and activate in the print window, the machine springs into action. A combination of onboard preset action and tasks specified in the top startup G-code from the job file trigger the mechanical system to move elements around in the operational envelope. It sets out to accomplish these two critical tasks. One, the homing of the XYZ axis by moving the tool head and the build platform to hit the corresponding XYZ stops. From this point forward, the control system knows where the tool head and build platform are and calculates all adjustments going forward from this known position. Two of the triggering of an auto leveling script that probes several points on the build plate to make slight adjustment to each aspect of the motion telemetry. This helps to make sure that the build plate, the area that the nozzle on the tool head can access, is true to the manual calibration of the build plate. If the difference is too great to make small compensations and adjustments, the interface will display an error message requesting that the operator run the requesting an operator to run the manual build platform calibration process to improve the baseline calibration before trying again. When you bring Together, the results of both of these activities, the in-stops identifying the true 0 points and the plate calibration probe ensuring that the nozzle will always be at the right distance from the physical plate. The build envelope is established and all is set for the print to begin. Now when the right temperature and condition have finally met, in just a few more seconds, here we go, here at the end of the startup sequence. The machine goes into motion again, moving the tool head, the build plate, purging some material and then finally heading to the starting position for fabrication of the desired part. But we are going to leave the printing of the object for the rest of our days through the anatomy of 3D printer. Okay, so now we are going to start our deep dive into the core systems that make up a desktop 3D printer. While looking at the control system interactive interface, the units we are using have an onboard interface. But remember that the device doesn't need this feature in order to be considered a 3D printer. Many entry-level and DIY kit options forego the interface to save on cost. But enough of these assembled desktop printers offer one, now that it has become standard practice. These interfaces are the primary controls you will use to calibrate, operate, and service your printer. In some cases, the interface complements the computer controlled advice. In others, it replaces computer control entirely. What the interactive interface subsystem is and isn't within the control system. The interactive interface subsystem is the first of the subsystem and components will highlight. The interactive interface subsystem is a set of control and display elements on the 3D printer hardware itself that allow an operator to communicate to the control system. Well, it communicates to the control system electronics and calibrate, operate, and service the printer. The role of interactive interface is to move the access point for a majority of the features you need from within the heart of the printer's electronics on out into the component seated on the device itself. This accessibility proves essential for basic print job setup configuration and moving that operation of an external computer. Even though the interactive interface is the element you can see and interact with the most directly, hence its name may separate from the central electronic control board subsystem. In the case of an Ultimaker 3, rather than being managed by electronics control subsystem, the interface subsystem communicates with the outer view embedded system and printer control board functions. Interactive interface. The primary function of the interactive interface is to provide a means to operate and receive feedback from your machine before or during and after the print. Another critical function is to provide a means to calibrate and configure elements that cannot be automatically sensed in position by the machine itself. A third function, as a service panel, to allow you access to core utility functions such as setting up networking access, updating and reverting firmware, and reverting user assignable settings to factory default. Components control display, job delivery in the case of the Ultimaker 2 Plus and 3 families. The interactive interface system has been widowed down to just 3 primary components: control toggle, display and fault delivery. To operate the subsystem, you can navigate through the menus and submenus by rotating and pushing the button on the right side of the display. Rotate to select, push to activate, as minimalistic as the interface is. Feedback details such as blinking LED under the Ultimaker 3 button can add an intuitive user experience. A blinking button means that Ultimaker 3 is waiting for the user input. The interactive interface system on your printer might not have the real estate you're going to use to your laptop, tablet, or even smartphone. But by breaking up options into multiple nested menus and operations, you can squeeze quite a bit of behavior into a few lines on the LCD characters display. For example, the display on this Ultimaker 3 offers three submenu options on the primary boot menu. Print. This allows you to select a file to print from your USB thumb drive. Displays a few details about each print option as you scroll through them, and offers a menu while printing that allows you to tune the print settings or even abort the print entirely. Material or print core. The material print core submenu allows you to load or unload materials and print cores, as well as run a number of the on the fly utilities to move the materials and tweak the baseline print temperatures. Here are the areas of the interactive interface I recommend you to explore for every machine before using. How to start a print job, how to pause or abort, and in a hurry, how to calibrate and configure your machine to use with a specific material, what nozzle to use, yeah, environmental conditions, how to monitor your print, and what alerts you should watch for, and how to reset your machine for the next user. Often all the critical elements you need to know can be picked up at a glance with a resource instead of sorting fruitlessly through the menu item after menu item, uncertain which options lead to what settings and all those. So the next time you're standing in front of an unfamiliar machine, take a moment to flip through the menu or search online for details that can make your experience more pleasant and successful. Okay, so now moving on to our next topic. Well, thanks to the popularity of a symbol of desktop 3D printer these days, an average printer operator rarely spends much time with the physical electronics unless faced with the problems to address. A component that craters on the PCB, a connection that becomes loose, or a new wire harnessed to route through the body of the printer. Though of us who got started with desktop 3D printers when they were kids have spent much more time with this critical system. Even those of us without much experience designing circuits have found the experience helped to inform our understanding of the machine as a whole. Let's spend some time taking high-level overview of the boards on the Ultimaker 2 Plus. While the electronics vary from manufacturer to manufacturer thanks to some early fields of standardization around microcontroller, firmware, stepper motor, temperature sensor, and other basic components, there are many similarities from vineyard vendor. Critical node in the nervous system of your printer. Within the printer, the control system plays a critical role in the operation of your printer. The central subsystem of the control system is the control board itself, which can also be called the motherboard. Logic board or main board depending on the vendor and your preference. My preference in these in these days is the control board. While it is tempting to call the control board the brain of your printer and compare it to the CPU of your laptop, this isn't the brain of highly evolved mammal. Think of it as a brain of an earthworm or other primitive life forms. The board does not send and receive a range of inputs and outputs, but no complex analysis nor complex decision making is happening on the fly. The critical instructions for what happens during 3D printing is driven by the G code job file, which is prepared ahead in the time of the computer. The control system executes those instructions, which are the primary roles of the control board subsystem. The electronics control subsystem primary roles are to keep time and execute instructions written in the G-code files before the job begins, and send them and receive power and communication pulses that impact all the other aspects of the machine. The electronics control subsystem secondary roles are to synchronize timings after other electronics driven components such as the daughter boards like the interface, auto leveling sensors, and hidden build platform electronics, and to route communications and power to the secondary electronic system as well. For popular approaches, the subsystems and components of the control board element can vary widely from vendor to vendor. So instead, let's explore four common approaches for how to set up the electronics in the desktop 3D printer. Some printer will build up electronics as a series of separate components and control boards patched together via lead wires and various extension cables and wire harnesses. This might allow machine designer to avoid the development time and expense to design, produce, test and manufacture new electronics. But at the cost of putting far more of the electronics burden on the shoulder of the end user, it's worth mentioning that this route exists, but it has fallen out of favor for all the individual machine. As it becomes easier and easier to run custom PCB is even in small quantities stacked modular electronics packages. This has been the most common approach in the RepRap movement, and thanks to the role of RepRap, the evolution of desktop 3D printing in general, you will still see the examples of this solution out in this field. For stacks, modular electronics, you generally start with a popular and trusted developer board like Arduino Mega or BeagleBone Black that houses a microcontroller, which is at Mega, and produce a shield to add components and routing to allow you to drive your printer. The stack doesn't have to end there either. You can then add breakout boards and allow your control board to manage stepper motor drivers, extruder controllers, and more. While this approach allows you to stand on the shoulders of the other electronics engineer and manufacturers, not all users, even intermediate ones, have the proper skills and equipment to install and repair subcomponents without damaging the elements. One of the control board as a hardware development world continues to expand with more affordable routes to affordably fabricate custom PCBs. Many manufacturers create their own all-in-one control boards. Many of these take advantage of opportunity to incorporate elements from open source development boards so that they do not have to start from zero. Every machine, the main disadvantage are the development times and cost and minimum order quantities that can make even minor design and manufacturing mistakes very costly. Electronics managed by embedded system. Lately, a fourth element in gaining traction, adding an embedded Linux computer into the mix and reapportion the various tasks and systems between the motherboard and the embedded system. We'll explore one example of this using the Ultimaker 3 electronics routing, a PCB2. In the case of the Ultimaker 2 electronics, the 3D printer control electronic subsystem consists of a main board, power supply, and routing, XYZ stepper motor controllers, extruder motor controllers, heat brick and print part, cooling fan controllers, heater, and temperature. Well, there are many more like monitoring controllers, bed heaters, and temperature monitor, XYZ in stops, case LED strips, and interface with any daughter boards such as interface board. First, let's start with the power brick. Well, power brick is a power electronic device which converts AC into DC power to deliver into the electronics for the distribution across the system. Next, the widest spread but less obvious component of the subsystem is the wiring itself. Like the traces on the main PCB, the hookup wires and harnesses are bringing all the electronic components into communication with the microcontrollers at its heart. Because of a hookup wiring, it is possible to physically move the outboard electronically powered and communicating components right to where they need to be. Third, they use USB connection, which is while visibly large, which is while visible largely as a USB port on the back of the machine. Is its own subcomponent managing USB to serial communications so that it is possible to program firmware and control the machine externally. What helped me master machines in the past was simple act of routing all the cables and patching them into the corresponding ports on the board. At first, the silk screen abbreviations and mysterious components populating across the PCBs were more of a game of memory matching like with from the instruction. But given that there are a lot of similarities from vendor to vendor, it's worth looking at the routing from Ultimaker 2 mainboard electronics from an Ultimaker 2 Plus to help orient out how this board connects into the other components in the machine. In cases like the Ultimaker 3, a more computationally powerful embedded Linux system has taken over a majority of the central management position. The microcontroller driven subsystem continues to play a critical role. But now, several of the elements of the control electronics can now be split and monitored in parallel by the Linux system. Okay, so this was all about the frame, case, and closures. So I hope today's class was helpful to you to understand more about 3D printing. Well, today's class was more about in depth about the control system and the mechanical system that are involved in 3D printing. Well, we have now the designing part. Okay, so let's move on to our designing part. Okay, so for designing, right now we are going to use software from Autodesk, which is uh, known as Fusion 360. Okay, so what Fusion 360 does is it will. Okay, so yeah, yeah. I hope you can see my screen. Okay, well, this is the Fusion Autodesk Fusion 360 screen. Well, this is the work plane where we have to design our stuff. So today, I think we can design some kind of desk organizer or a pen stand, right? Okay. So, so let me just go to how to design something in Fusion 360. So first of all, why we are designing? Okay, the 3D printer requires a job file, right? So that job file will be provided by the slicing software, and that slicing software needs this Fusion 360 or any kind of CAD software. You can also use Tinkercad if you need to. Okay. So, okay. So let's start by designing. Okay. So first, let's start with a pen stand. Okay, the pen stand itself. So first, I will use only the basic commands to make a pen stand. Okay. So first I will go to create. I will create a sketch, and then I will select my plane. For 3D objects, there are three planes: the X plane, the Y plane, and the Z plane. If you want to know the XYZ planes, well, you can see in the origin itself. See here, it's an origin plane. In this origin tab, you can click, and then you will get the X plane, Y plane, Z plane. Always will be the point X, Y, X, Z, and Y, Z plane. Okay. So right now I'm going to select the XZ plane, and now I will be designing a pen stand. Okay, so I would like my pen stand to be in a square or in a rectangle shape. It's a desk organizer, right? So I will use a 2-point rectangle. Okay, so I think we should use a center rectangle. We'll use a center rectangle and I will draw a rectangle. See? Okay, so now the dimensions. But here the dimensions are in millimeter scale. So, well, we know 1 centimeter would be 10 millimeter. So I need my box to be uh, around 5 to 7 centimeter, 5 by 7 or 6 by 7 kind of. Okay, so let's make one side 50 mm, which would be the 5 centimeter, and let's make the other one 70 millimeter. Okay, so right now we have set our constraints. We have built a rectangle. Okay, so now what I will do, this is the 2D plane, right? This is a 2D plane. I will click on the finish sketch. Now you can see this is a 2D plane, right? See, this is a 2D plane. It's just like drawing on an A4 size sheet or any book, right? Okay, so now what I will do is I will go to modify, as I have to modify this 2D drawing. Sorry, I will go to create and then I will select extrude. There's a shortcut also by selecting the E keyword. Okay, now I have selected extrude. Now I have to select which plane I have to extrude. So I have been selecting the plane on which we have drawn. I have selected that plane. And now there is an arrow which we can push upwards or downwards in our desired location. Okay, so right now we can see the distance from where it should move. Okay, so I need the height to be around, let's say, around 60 millimeter. So I can click on this distance and I can change it to 60. I think 60 is too big, so let's go down to 50. Okay, and right now by going to home position, you can see we got a rectangle, right? Okay, so one thing that I would want to do is select this plane, I mean the top plane. Well, you can see here top. Okay, so I would like to draw on this top plane right now. I will select the rectangle from create sketch. I have to select this plane, go to create rectangle, and I will select center rectangle. And now I will just make a rectangle here. Or otherwise, what you can do is there's a one more easier way. See, you can make a rectangle like this, and you go to finish sketch, go to finish sketch, and then you can extrude it down. How? See, like this. See, it becomes a container, right? Okay, so like that also we can do. Otherwise, I would like to do it in some different manner. I'll show you how. See, here are the sketches available that we have drawn previously, right? I will select the sketch and I will just enable the sketch. Right now it's disabled, you can see here. I will enable it. I will go to down and see here I've got my sketch. Now what I'll do is I will go to create sketch, and I will select the keyword O, which means offset. You can see here offset. Okay, so right now I will select this plane. I have got this sketch and I will make an offset of this plane. See, and right now it is equal from each and every side. You can see here it is 1 millimeter. Here also it is 1 millimeter. Here also it is 1 millimeter. And this side is also 1 millimeter. So I need the thickness of my pen stand to be 2 millimeter. So what I will do, I'll put my offset position to 2 and click OK. So right now I've got this position also. And what I'll do is finish sketch. See, I got another drawing. Now what I'll do, I'll click extrude. Okay, you can also do the extrude process from clicking create and then extrude. Now I'll select the plane. I'll put it down to about I know we set it around. Okay, this would be enough, right? I'll click OK. And right now we can see we got a container type of image. Okay, so I have to add partitions to this. So what would be the next step? Well, I have to like make it in 3 partitions. So what will I do? Okay, so I have to draw it from again, right? I have to first draw the 2D image, then I have to extrude and make it a 3D design. Okay, so as I have said, I will only be using the most simplest tools here. I won't be using any kind of complex tools. Okay, so just doing that. Before doing that, I would like to introduce to an much more newer tool which is known as fillet. You can see here just fillet where the keyword is F. So you can press this F and you can see these are sharp edges, right? So we can smooth these sharp edges. I'll show you how. Now see, I've clicked upon this edge, I've clicked on this edge. So like that I can click on many edges, as many edges as I would like to add this fillet. Okay, so now I've selected all the sides and you can see what I'll do. I'll add this fillet. You can see what is happening, right? The edges are becoming smoother. Okay, so I'll just add it to around 1.5. Okay, the 1 is enough. Okay, 1 millimeter of radius. I have selected OK. Now you can see it is smooth, right? Okay, so now what I'm going to do is I will draw the subsections for this container. I mean for our pen stand. Okay, so I'll select the create sketch command. I'll select this plane. Okay, so after selecting this plane, I will select. Well, you can use as many ways if you want to. You can use line, but I will use rectangle. Okay, so by selecting rectangle, center rectangle, and then from here I will select the distance that I need. I will select it as 2 and then hit OK. Okay, and then I will divide this part into 2 more parts. So I will then again also go to rectangle and select center rectangle. Okay, I think the 2-point rectangle would be enough for this. Okay, so I selected this 2-point rectangle. Okay, I've selected from there. I have to make it 2, right? Tab and 2. Sorry, 2. This can vary about 2. Wait. Okay, so we got it. So right now we have got 3 parts, right? Well, we can see there is an overlap over here, right? So I can remove it by using the trim option. Okay, from here constraints, I can use the trim option. So well, there is also a shortcut for the trim option, which is T. So I will press the T, and what I will do is I will select the line which I don't need. See, I have removed that line. Okay, so right now we have got our pen stand ready. Now what we have to do is just extrude. We have to finish the sketch first, and then we have to select this extrude. Now selected this extrude, I'll select the drawing which I have just drawn, and I will extrude it upwards. See, it's as simple as it looks like. Okay, I'll just stop it over here. Now what I will do is, you can see the base is also sharp edges, right? Here it is sharp edges, sharp lines are going over here. So I will use this fillet option, and I will select this. Okay, and then add a fillet. And then hit OK. Now you can see we got our pen stand ready. Right? See, it's as simple as it looks. Okay, now I would like to require something from you guys. Okay, well, it's simple. I want you to name this pen stand. You have to give a name for this pen stand. Let's see who is creative here. Yeah, well, I will share this video in the YouTube. Okay, so you can see this in the YouTube also. Okay, yeah, I can add thickness, but 2 mm is kind of okay for now, as we would require this to finish as soon as possible. So in order to reduce the printing time, I'm doing this. Okay, so can you just provide me a name so that I can engrave it on? Well, by engraving a name, we can make it a custom pen stand. No. Okay, let's see for creative name. Yeah, come on, guys, we have only 6 minutes left. Okay, so Nikita has answered Phoenix. Okay, so let's name it as Phoenix. Okay, so what we have to do is we have to select create and then create sketch. From that menu, we have to select the text, right? First of all, we have to select the first of all, we have to select this plane. Okay, so I have selected this plane. Okay, before doing that, see that when I press this home button, it is tilted. Okay, so first what I have to do is I have to move it. I have to rotate it, right? So I will select this and I will rotate it 90 in 180 degree. I'll hit OK. Okay, so right now it is okay. So I will go to create sketch. I will select this plane and then I will go to create and I'll add this text. See? Okay. So after selecting this text, I will place it over here. The name Nikita told us, the Phoenix. Okay. So I'll add this name and just put it over here. Okay. And what I do is I think it's okay. So just I think I just make it bolder. Okay. So this seems okay. Right now what I'll do is I'll hit OK. And well, one more thing, you can use any kind of font which you would need to. Okay, there are indefinite number of fonts that you can use to engrave a name. So right now I'm using default Arial and I've entered the name. Well, I think if all are in caps, then it would be right. Okay, so we got the name here. I'll hit OK and see we got our name engraved. So this is not a 3D yet, right? So what I'll do is I'll select finish sketch and then I'll select extrude and I'll select this plane. And what it will do is you can see, right? See, it will engrave it. Okay, so if we put the height as 2 millimeters, so I want it to be just 1 millimeter. So yeah, it will be okay. So I'll hit OK. See, we got our name Phoenix over here. See our design, our pen stand is ready. Okay, so one more thing which I would like to say is we can export this thing. Okay, so it will be in bodies. You can select this body, right? I will right click it. I will select save as STL. STL, as I mentioned in the previous classes, was stereolithography, right? So I will save as STL. Okay, let me just open the slicer, which would be Cura, which is an Ultimaker, software. Okay, so it is asking me to select the refinement and to preview the mesh. Okay, so I don't need to preview the mesh. So this will be our mesh. Okay, so I will just save it in the desktop and name it as pen stand. Okay, I'll hit save. Okay, so right now I have saved the files and I'm just waiting for my slicer setting. I'm just waiting for my slicer setting to open. Okay, let's wait. Okay, so do you guys any kind of do you have any kind of like questions or queries to ask? Well, I'll try to answer it right now until this Cura opens up. I hope you guys can listen, right? Okay. Yeah, we can use different softwares for designing. I mean, there are many. We can use SolidWorks, we can use Blender, we can use Fusion 360, we can use Tinkercad. Well, Tinkercad is uh, much more easier to use. Yeah, not only Fusion and Tinkercad, well, you can also use SolidWorks. SolidWorks is kind of like more hard. Okay, so the Fusion 360 is kind of simple. It is the most advanced version of any CAD software available. Well, one of the main advantages with Fusion 360 is that it is cloud. It is fully cloud based. You can see here in the design, we can have design session, we can render the object, we can add animations, we can do simulations, we can do the manufacturing, which is the CAM, okay, computer added manufacturing, and we can also have the drawing. So okay, so here the Cura app has been opened. Okay, so I'll just share that screen to you. Share. Okay. Okay, here. Okay, so here you can see this is the Cura interface. And right now what I'm going to do is I'm going to add the files. Okay, the STL files. And I'll just drag and drop it. So you can see our file, right? This is our file. See, Phoenix has been engraved on it. So what I'm going to do is I'm going to rotate it first in 90-degree. I'll make sure it is okay. Okay, so I'll select my layer height. I need it to be 0.2 millimeter. I need an infill to be about 30%. Okay, and there is no support required and no bed adhesion required for me. Okay, now I will slice it. Okay, so now you can see it would require 4 hours and 55 minutes to print this one thing. We can also preview it layer by layer. Okay, so let's see. Right now I have zoomed it in. Okay, and I'm going to see it layer by layer. See, this is how 3D printing works. It goes on by layer by layer, layer by layer. See, well, you can also see the print head in movement. Okay, where if you push that play button, you can see this nozzle, right? What this nozzle is doing, you can see this, how it prints. This is the live printing in action. This is how it will start. It will start by drawing this layer by layer by layer. This is known as the additive manufacturing. See how it fills. And like this, it will go up layer by layer, up, until the final G code is been received by the control board. And here it finishes the print. Okay, so that was all about today's class. I would like to have a feedback session with you guys right now. Okay, Mohan Raj asked one question, but we need to change in STL file. Uh, the STL file, yeah. See, the Fusion 360 and Tinkercad both are cross-platform devices. It can export the design files into various forms. It can export as a F3D file, as an OBJ file, as an STL file, and many more. So STL file is what used for 3D printing. Hemant asked how the materials be tested and analyzed before going on 3D printing. How the part design be tested. Well, if you need to know the material strength, the tensile strength, and all those are available with the filament itself. Okay, you can see the filament manufacturer's website and get more information about the strength and stress. All the details would be mentioned over there. And if you want to know about the design you made, well, in Fusion 360 there is an option of simulation. Okay, it's in the paid version, but you can analyze the stress and strain characteristics over there. No, the slicing and meshing are not the same, but they are kind of interconnected to each other. What slicing is just okay, you just consider how to make something layer by layer. Okay, just consider a stack of paper. Okay, well, a stack of paper is only made when you add those paper one by one. Okay, layer by layer. So that's how slicing is done. Okay, it just makes our 3D model into layer by layer. Lalit Kumar asks, what is adhesion? Okay, well, adhesion means the build plate adhesion. Okay, every 3D printer, each and every 3D printer have its own build plate. There are heated beds also. There are glass plate beds, fiber beds, many kind of beds available. There are metal beds also and glass beds. Okay, so what adhesion means? The first layer of your 3D print should be well stick to the build plate. Otherwise, it won't print. Well, it will print, but the printing would be, the finished product would be not that good. Okay, so the build plate adhesion should be a must. Well, the first layer should be properly sticked to the build plate. If you are using an ABS, then you would require a heated bed because the ABS works at higher temperature. It works at the heated bed should be around 110 degrees Celsius, and the nozzle should be at around 250 to around 300 degrees Celsius. If you're using PLA, then you don't need a heated bed, but still, if it needs to stick properly, you can either use a glue stick or you can use the heated bed option. Can room temperature affect the filament while it is pouring in? Well, no, because the room temperature can affect the time that it takes to heat it up. Okay, the power supply will work continuously to heat the bed and the nozzle continuously. Well, there is a feedback system in that. There are temperature sensors which will sense the current temperature. If it is less, then it will give the command to raise the temperature, and if it is more, then it will give the command to the control board to stop the rise in temperature. Well, the humidity can affect the filament. Okay, that's one thing that I will discuss later in our training sessions. Okay, so I hope the class was interesting and much knowledgeable to you. I would like to have the feedback sessions in the Google Classroom over there, and I will post few reading items over there. Okay, so I'll just save this file and I will go and record the 3D printing for you. So tomorrow we can see how the 3D printing has worked.